Hello, 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 hello. Today is still March 7. It's the birthday of my countryman, the famous artist Piet Mondrian. Yeah, it is still March 7. It is 6 minutes before midnight, by the way, but still his birthday. So the solutions to this problem will also be in honor of Piet Mondrian. Just before I started recording, my wife made me some hot chocolate, and she can make hot chocolate like no one else in the world. So allow me to take a sip of her hot chocolate before I start the solutions. Oh my goodness. Oh my goodness. This is magnificent. This is so nice. It's because of my wife, but maybe also because of Mondrian, that it is so delicious. All right. Here is a very thin shell conducting sphere. The sphere is neutral, has no charge. But I put inside the hollow sphere a charge Q at this location, and this charge Q cannot move in any way direction it wants to, so it is constrained. The charge Q is closer to this side than it is to this side. This is 2/3 the radius, and this is 1/4 the radius. Here's a point A and here's a point B, and this point is half a radius away from the surface, and B is half a radius away from the surface. And the question now is, what is the electric field at A and what is the electric field at B? So keep in mind that Q is closer to A than it is to B. You ready? Let's assume that Q is positive. If you want to make it negative, be my guest. Conceptually, there will be no change, of course. I will give this charge plus Q. I will put that charge on a conducting sphere. It could be a very small radius, but not 0. Maybe 1/1000th of a millimeter. You will later understand why I do that. So, this very small sphere is here, and the electric field lines emerge from that very small sphere, radially outwards, perpendicular to the surface of that sphere. Keep in mind, remember, that if there is no current going through a conductor, at the surface of a conductor, the electric fields must be perpendicular everywhere to the surface. If there were any tangential component, the free electrons would move to kill that tangential component. So the E fields emerge perpendicular radially outwards to that surface. Due to induction, the inside of our sphere will get a minus charge, which is exactly the same in magnitude as this charge. So it will get a minus Q charge. The E field lines that emerge from this teeny little sphere must hit the inner wall at a right angle. The E field must be perpendicular. So this angle is 90 degrees, this angle is 90 degrees. Every angle here is 90 degrees. And so you have a very interesting pattern of field lines. And it should be obvious to you that the surface charge density on the inside here, negative charge, will be larger than the surface charge density of negative charge here. Because Q is closer to the inner wall here than it is to the wall there. Since the sphere was neutral, clearly there has to be a plus Q charge on the outside surface, so that the net charge on this large sphere is 0. So there has to be a plus Q charge here on the outside. And now the question is, what will be the charge density on the outside of my sphere? I invite you to watch my lecture 6 of 802. Take a look at it if you have time. When you have an equipotential and all conductors through which no current is flowing are equipotentials. When you have an equipotential, a conducting object, here is such a conducting object, very strange shaped, and I place charge on the outside on that surface. It's a solid piece. Then the surface charge density on this surface here is proportional to 1 over the local radius. The local radius here, this is a flat surface, is almost infinity. The local radius here is much smaller. So the surface charge density here will be high here, will be very low here, and in between here. The E field at the surface, outside surface, always perpendicular to the outside surface, is the surface charge density divided by epsilon 0. All that is part of my lectures. Now comes the shock. Maybe it's a shock. Take our sphere. Our sphere everywhere has the same radius. So that means that the surface charge density everywhere on the sphere is the same. So, if the surface charge density everywhere on the sphere is the same, then the electric field on the outside surface, at the outside surface itself, is also everywhere the same. And the remarkable thing is that that is independent on the location of Q. Isn't that a surprise? So whether Q is here, or there, or there, or there, as long as it is inside this sphere, the outside world cannot tell what the location of that charge Q is. Regardless of where the plus Q is, the surface charge density on the outer surface is everywhere the same, and with Gauss' law, we therefore find immediately what the electric field is at the surface on the outside. We take a closed surface, which is the surface itself, the outside surface, 4 pi r squared times that, the magnitude of that E field is Q divided by epsilon 0. So here you have the E field right at the surface. What now is the E field at the point which is 1.5 radii away from the center? Whether it is here or whether it's there, or whether it is here, or there, or here, as long as it is 1.5 radii away from the center, it's everywhere the same. So with Gauss' law, you have to replace this r now by 1.5 r, 1.5 times r, and so the E field becomes this. See, r squared is 9/4, you lose the 4, so you get a 9 here. So this is the answer to the problem. The E field at A is the same as the E field at B, in my case radially outward, and the magnitude of the two E fields is the same. I would now like to add a few words about electric potentials, because many of you have difficulty with the concept of electric potential. This sphere is an equipotential. That means the electric potential everywhere on the sphere is the same. It's the same right at the outside of the sphere. It's the same as inside the metal of that sphere. Since the electric potential at infinity, we define that as 0, the electric potential right here at the outside is the integral of E dot dl in going from r equals capital R to infinity. And when you do that integral, which of course I do in my lectures, the potential at that point is the E field at that point times the radius at that point. So, if you had the E field at this point, you multiply that by the radius, so this r squared becomes an r. That is the electric potential at the outside surface. Inside that surface, even though it's thin, it doesn't matter, even if it's thick, the E field is 0. So the integral of E dot dl through that surface is 0. So there's no change. So the entire metal is at the same electric potential. Now comes the question, what is the electric potential inside the sphere? That's a different story. So we know the potential of the sphere, we just calculated that. So what now is, for instance, the potential, electric potential at this point? Well, I can tell you what the difference between the potential here is and the potential there. Since you know this one, you know this one. The difference is the integral of E dot dl in going from this point to the sphere. Whether you go this way or whether you go this way makes no difference. You will always find the same answer. So it's clear that the electric potential here is lower than the electric potential here. Because the electric field close to plus Q is here much higher than it is there. And so as you get closer and closer to this charge plus Q, the electric potential inside the sphere will go higher and higher and higher. Why did I give that plus Q charge? Why did I make it a small sphere with radius maybe 1/1000 of a millimeter? Well, you can calculate now the E field at the surface of that very small sphere. I just told you how to do that. What would you have found what the E field is at that location if the size were 0. If it were a point source, then the E field right there would be infinitely large. And we can deal with that. College physics books in general don't address that issue, but it is a key point, of course. So for me to give that charge a finite size, sphere with an extremely small radius, the E field right at that surface is not infinitely large. And so I can calculate now also the difference in potential energy between that inner sphere and the outer sphere by doing the integral of E dot dl. Okay, that's it for now. Oh my goodness. It's March 8th. It's no longer Piet Mondriaan's birthday. Well, I still would like to end, in honor of him, a sip of my delicious hot chocolate. So it's still here. Hey, it tastes differently. Why is that? It doesn't look like Mondriaan anymore. What happened? Oh, of course I know what happened. It's not Mondriaan's birthday. And the cop knows that. Have a nice day, take care. And of course, we'll be friends. It's my time to go to bed, by the way. Hello, 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 hello. I just woke up. It's March 8th, so no longer Mondriaan's birthday. So last night, just before bed, I showed the Mondriaan solutions to my wife. And when she saw this drawing, with the plus q charge here, and my statement that on the inside of the hollow sphere, through induction, there therefore has to be a charge minus q, she said, I trust that, but isn't there perhaps an easier way to see that? And of course there is. Inside this material, it is very thin, but it has a finite thickness, of course. Inside that conductive material is no E field. So if now you make a closed surface, sphere, inside the material and you apply Gauss' law, then the closed surface integral of the electric flux going through that surface is the charge inside that surface divided by epsilon 0. But since the E field is everywhere 0 inside the metal, there is no flux going through that closed surface. Therefore, the charge inside must be 0. And therefore it is required that the charge that builds up on the inside of the wall must have the same magnitude but opposite polarity as the plus q. So that may be an easier way for you to see it. On another issue, now that I'm at it, as long as you're outside the sphere, the electric field falls off as 1 over r squared. Not inside, but outside. And the electric potential falls off as 1 over r, because you have to multiply the electric field at position r times r. Last but not least, many of you will say, haha, Walter Lewin played games with us. He first showed a Mondrian cup that was beautifully colored. And then he had another cup which looked similar, which is not colored. So some of you may think that I changed the cup. It's not true. I'm very honest with you. The cup that I showed you, with the hot chocolate inside and the beautiful colors, is the same cup that I showed you at the end of the solutions. Did the colors change to black because it was no longer Mondrian's birthday? I don't think so. But they did change to black. Think about it. Maybe you can come up with a solution. Alright? Have a nice day. Take care. And surely we'll be friends. I'm about to take a shower. I just got out of bed. I'm still in pyjamas. Oh my goodness. I still haven't mentioned the numerical results. The charge is 3 microcoulomb and the radius of the sphere is 6 centimeters. 1 over 4 pi epsilon 0 is 8.99 times 10 to the power 9. So I always take 9 times 10 to the power 9. So I then find that the magnitude of the electric field both at A and B are about 3.33 million volts per meter. Sorry for this very long solution, but I hope you've learned some physics. Bye.